Hey everybody, thanks for joining. My name is Fabio Casati. I am a principal machine learning engineer with ServiceNow. And today I'm going to talk to you about enterprise AI autopilots. So the point I want to make is that, we keep hearing in the news about, the great progress of AI, and we're under the impression that every company is rushing to adopt AI. And to some extent that is true, but I think that's happening at a much slower pace than everybody anticipated. And part of the reason for that, and let me put this as a provocation, is that as a community, we've been focusing a lot on precision and accuracy. And to some extent that's good, but I think we overstudied that topic with respect to other topics which are really fundamental for the adoption of AI, which is helping users on the journey to understand where, how, and why a specific AI technique can be used inside their business processes, right? And also, once you do that, how do you take them on the journey to adopt, prototype, test, and put in production a software program that is really probabilistic in nature and not deterministic? And that's really something companies, are not used to, right? It's something new. And it really requires an entirely new mindset for how to approach the problem. So in this talk, we'll discuss some of this topic, and we'll also walk you through some simple ways in which we can abstract and scope part of the problem to begin to make meaningful progress in this field. So this slide shows a study by McKinsey. I think the study is not super recent. At this point, I think this data is a little bit over 1 year old, but I think it paints a really interesting picture. So what the number is saying is that the percentage of companies, actually even the most digitized company, that have adopted AI in 2 or more of their processes is actually pretty small, right? I think now things are changing recently. I think the trend is towards a very rapid acceleration of this. Nevertheless, these numbers I think are way behind what everybody anticipated, and especially I would say way behind the feeling that you get when you hear about AI in the news, right? And there are many reasons for this. McKinsey in the same study, also tries to uncover some of these reasons. And I think the answer are, kind of what we expect them to be. It's like not every company has a team of data scientists ready. Not every company has the data required to support inferences that are useful for their business, right? A very clear idea about which problem we want to solve, and how we go about solving it, right? So that's really the first thing. And this is already, not tough, because there are zillions of problems we could be tackling, right? And we need to find what is the low-hanging fruit for us, right? And then, of course, once we have a problem, we also need to think, do we have the right data that can help us train, useful models that will take us to wherever we want to go, right? Which leads us, I think, to the next and probably most important question, which is, where is it that we want to go, right? So sometimes we assume as researchers that we picture in our head that companies have a super clear idea about how the processes work, and they know exactly what are the KPIs, and they know exactly how to measure them, right? And therefore, it's going to be very easy for us to say, okay, if we put AI, we go from here to there, right? But that's actually not the case. So very often having an understanding of how your current processes work, it's a hard problem by itself, right? And because sometimes you don't have a clear picture of the as-is state, then this makes it really hard to sell something completely new, to say, hey, we need to go from here to there, right? Because you really don't know, or you may not know exactly what is your starting point and your starting quality, right? So this makes the sale a little bit harder, or actually much harder, right? And then, we're introducing something really new. So we're introducing a probabilistic computing model in the end, right? So this means that we now have software that, yeah, hopefully very often we'll get it right, but sometimes it gets it wrong, right? And sometimes it's even giving two different answers to the same question, to the exact same question. And this is something new for most people. This is something certainly new for, software engineer and for software tester, right? So it's somehow hard to get your head, let's say, around it, right? And this, by the way, also incidentally means that calibration is, I would say, is as important as accuracy. So yes, it is important to get models that carry high precision, and that's where most of the research is focusing, but it's also very, very important that the model can estimate the confidence for each prediction, right? Because this gives the downstream task the chance to say, okay, I'm going to trust your prediction because you're going to tell me that it has very high confidence, versus you are telling me you're in doubt. I'm not going to use your prediction. I'm going to fall back to some default or to some rule, or I'm going to ask a person, right? So calibration is really, really important, right? It's almost as important as accuracy. And then, of course, we have now this new kind of software. How do we maintain it? Do we retrain the model? How often do we do that? Do we test the model after retraining? Where do I test it? Do I test it in a lab environment, in a test environment? And is the data the same in my test environment as in production? So all these questions will come up when you try to put AI in production, right? And then, of course, there is the big question about fairness, right? So one of the good things about the AI landscape lately is that people are asking this question more and more, right? And the problem is huge. It has many subtleties, many angles, but at least, communities and companies are starting to ask themselves the question, and this question needs to be answered before, we put a new model or method in production. So what we call the AI autopilot, or Metha AI, is AI and in general methods that take care of the initial part of the ML solution pipeline, which is exactly the point where we study and help users understand which problems they can and should solve with ML, and also help them to understand what are their baselines and how accurate and how precise ML models should be as a minimum, so that they can actually benefit from them. Now, this problem space is clearly huge. I think we can think about hundreds of PhD theses working just of this, right? But I think there are ways to abstract the problem so that we can work on it and create solutions which are general enough to apply to a large classes of problems. But the abstractions are simple enough that we can actually make progress and come to measurable results, right? And one way to think about it is to consider our enterprise process as essentially consisting of a table which contains one record per process instance. So for example, if we're doing a customer support process, then we have our table where one record, for example, describes a customer request, right? And then this record will essentially go through a process that will correspond to changes in this value of the fields for this record, corresponding to our progress in helping customers with their request, whatever that is, right? And in this context of having a table and a process and possibly some metrics, then our goal is to understand which are the useful inferences that we can make, where can we add values, and then possibly help me understand what is the status quo, what are the meaningful baselines, how to measure them, and then to understand how good the ML models I'm going to build will need to be able to make useful contribution to my problem. Now, one way to tackle this problem and begin to attack this problem is to ask ourselves, okay, we have a bunch of fields which are essentially potential features. We have a bunch of fields which are potential labels that we may want to predict. We have a process over these features and labels, and let's ask ourselves, which are the columns we may want to predict based on other columns in this table, right? And in general, once again, this problem is also very large in scope because the possibilities are essentially proportional to the power set of the feature. So in any non-trivial table, and typical tables, have 50, 100, 200 fields, then the space of possibility is way larger than the number of atoms in the universe. So again, that's not a problem that we can tackle, right? Now, there are many ways to simplify this problem and to reduce the problem space by looking at fields and see whether these fields are actually eligible as feature or as a label for our model. And there are lots of different reasons why we may not want to use a field as a feature or as a label. And so, for example, very trivially, this field is often or always empty, and that happens actually in practice. Or this field has only unique value, so it doesn't make sense to be the output of a classifier. Or I can think about the exclusion based on the type. So for example, I choose not to consider images, or I can look at fields that are highly correlated, and I can decide to only keep one of them, right? Because they provide similar kind of info, right? So I won't go into more detail on this. Feel free to email me if you want more detail. The things I actually want to focus more on kind of the opposite problem. So the problem of illusions. And what do I mean by that? So an illusion is essentially when you believe that you can predict a label Y given one or more feature X, when this is actually not the case, right? And illusions are particularly, let me say, dangerous when I do not just believe that this can be done, but I train a model, and the trained model gives good results, and I test the model, and the tested model also give good results, right? And these are actually more common than you would probably think. And there are specifically three of them that I want to discuss here. One is the inverse causality. The second one is the observability illusion. And the third one is the end state bias, right? And as written here in the slide, a lot of them have to do with the fact that typically when you look at a table, you look at records, most of which are at the end of their journey, at the end of their life. So for example, just to keep with our customer support case, there will be completed customer support cases, right? But when you need to make predictions, you don't really need to make predictions on cases which are completed. You want to make them on cases which are just started or which are in progress, right? So there's typically a disconnect between what you find in a table when you look into it and what you want when you're actually making predictions. So let me explain these illusions through examples, and let's go back to our customer support process, right, and to our customer support table. One of the things in most cases you want to do and you want to apply machine learning on is the ability to predict to which group of people should a given customer support ticket be assigned, based, for example, on the customer request. Right? So you want to give it to a group of people that have the skills required to handle that specific customer request. And so what you will probably do is, you will start to, work on this table and build a model that can predict the assignment group. And an error we see that is often made is people trying to predict the assignment group based on the specific customer support agent to which the ticket was assigned, right? And yes, if you actually try this, and if you run this model through machine learning, you will get amazing accuracy, right? And if you still use this data, you just carve out your test data set, you also will have confirmation of the amazing performances of your machine learning model. Now, the problem is that you're working with an inverse causality problem, right? So in reality, what happens is that a ticket is first given to a group, and then within this group, later we choose a person, right? Not the opposite, right? So, but to find this out, you cannot just look at the table in a state, right? You would have to look at the history of each record and figure out that this typically happens. And therefore, it doesn't typically make sense to use the person as a feature to predict the group, right? And figuring this out is not necessarily trivial, or is less trivial than you would think, right? And once again, one reason why this is not trivial is because the person who is expert in machine learning may or may not be expert in the process and may overlook this, or may just look at what data is telling them and may triumphantly say that I have a great model that can actually predict the assignment group based on very high precision, right? The second illusion has to do with the observability. So we could build a model that, for example, predicts the duration of our customer support handling based on the group to which the case has been assigned. And this time it's not like before. So there is really a causal dependency between this, right? Because in general, certain groups may be assigned to deal with more complex problems, or problems that, by their own nature take a long time. So therefore, it's because we know that the ticket is going to this group, then we can make an inference about the duration of our customer support handling. But the problem is that, once again, if we look at the data, we triumphantly announce that, hey, we can make very solid prediction, a very precise prediction about the duration. But the problem is that at the time you would typically want to make those inferences, which is very often when a new case comes in, you don't have this information, right? Because you don't have the assignment group. Or maybe at the start it's just a dispatching assignment group. So a group whose purpose is to actually dispatch this ticket, right? And therefore you may not be able to observe the assignment group this ticket ends to, right? And therefore, yes, once again, when you look at your data and you're training a model and you're testing a model, you get great results. And it's only when you are in production and new cases start coming in, you find out, if at all, that you start getting wrong predictions. The third illusion we are considering is the end state bias. So what do I mean by that? So very often the profile of the distribution for a field is different between the start and the end. So we did mention some of this before talking about the assignment group. Very often, if you think about the assignment group, at the start, you will have a certain number of case ticket assigned to a dispatcher kind of group. But then when you go towards the end of the life, then you don't typically have dispatchers there, but you have the groups who actually have been working on the ticket, right? And very often the distribution of these groups at the end is much more flat and varied than what you get at the start, right? Which at the extreme can be that all tickets just go to the same group, right? And the same things can happen for other fields such as priority, because for example you may have the opposite case where you have a larger distribution of priority and urgency for tickets when you start, but then when you reach towards the end, hopefully you manage to kind of mitigate the problem, so you are unlikely to see, I don't know, cases that end with a very high priority, right? Because typically you would have found a way to manage them to some extent. So at the end, probably the urgency or priority would actually be reduced, right? So how do we go about uncovering such illusions? Well, there are, let's say, two cases. One case is when we have the logs, and one case is the case in which we do not have the logs available. So if we have the log of every change that ever occurred to our record, then things are a bit easier. We can, for example, look at the observability by estimating the density at the start. We can try to guess causal inference by looking at the order in which fields are changed. Right? At least we get a sense for it. And we can look at the end state bias by looking at how often, for example, a field changes from start to end. If it changes a lot, then we know that the end state representation of our records is not really, meaningful if we want to run predictions at the start. Right? So I will not discuss this further. Look in the paper if you want some more details. But this is the easier case. The more complex case is when I do not have this, this movie, which is the logs, right? So the logs they can be seen like a movie of my cases, right? So if I don't have this movie, then what can I do? Well, because I have a live system, then I can take photos. So I can take snapshots of my cases at different point in time, and through snapshots, I can try to reconstruct somehow my movie. Right? And to do this, you basically need a couple of things. One, you need to know, given a snapshot, you need to know at which point in the movie you are. So am I at the start of a case? Am I in the middle? Am I towards the end? Am I at the end, right? And there are a bunch of different heuristics that you can use to do this. The problem is a bit more complex than probably most people can think, but it can be solved, and I discuss some of this in the paper. And the second point is to understand how quick the movie proceeds, right? So trying to get a sense for how many photos, how far apart should be taken in order to get an estimation of this movie. And once again, I don't have much time here, but in the paper you can get a sense for this. Right? And once you do this in a smart way, it's actually surprising how good results you can get from taking photographs with respect to the case when you have your logs and the movies played out for you, right? So you see here some of the experiments I've done in different kind of tables, different kind of processes for different kind of fields, and you see what you get at the top of the top part of this table when you have the audit logs that are available, and in the bottom part when you just use snapshots or delayed snapshot, which is this technique I discussed in the paper. And you see that, while the results are not the same, the snapshot approach is actually, let me say, good enough to get a very good description of some of the illusions that you may have. And once again, I would like to encourage you to read the paper to get some more details. Right? So I put here once again my take-home messages, and we discussed them in the start. I hope they make more sense to you right now after we went through some of the material. And once again, we'd love to work on you on these subjects, on these topics, and create a community of people that is, working on this auto AI direction. And I'd like to thank you for the attention. If you have any question, please, send me email at fabio.casati@servicenow.com. Thank you very much.